Our next speaker is Dr. Rahimi. He's a specialist of artificial intelligence. We have few centers in the world competing in that field. You have Elon Musk, you have Google, and you have Dr. Rahimi. He has a PhD in electrical and computer engineering.
Thank you, Dr. Nozari. It's an honor and privilege to be here. This whole time I was sitting in the back, assuming after that talk, how am I going to give you guys as excited? So I'm going to stop assuming and trying to assess the situation. My talk today is about artificial intelligence, more specifically about human-machine symbiosis. Nowadays, we talk about artificial intelligence, different aspects of it, topics ranging from its capabilities, and also many would arrive at human-level intelligence or even superhuman-level intelligence. Today, I want to make a point that as we make machines smarter, we may just have a chance to create smarter humans as well. And in order to do that, we need to create an interface to our brain so that AI can interact with our brain. With that, the outline of my talk is going to be, first I'll show you some, how do I get at this? First I'll show you guys some capabilities of AI and show you guys what's the status of AI as of 2019. And then I'll talk about some measuring methods that we do for measuring mental states using artificial intelligence. And then I'll take a deeper dive into the technology behind artificial intelligence. And finally, I'll leave you guys with some direction as where we are heading in the near future. Is this, OK. So here I show some are the videos playing? This is supposed, if you press a tab on it. OK, so here's I'm showing some videos here. On the top left, you see a speed intelligence example of artificial intelligence, where the recent robots can actually assess the situation more than 1,000 times per second, something that is beyond human-level performance. On the top right, you see application of information surveillance reconnaissance, where AI in real time can assess up to 1,000 objects in the scene in a video signal and reason about where the people are, where the objects are, and what are the people in the scene are up to. On the bottom left, you see an application of AI in gaming. Nowadays, AI agents are playing game against each other. As a result, they have long beaten human performance since the 90s and in the recent years in the game of Go, which has board positions more than atoms of the universe. In the bottom right, it's the most cutting edge artificial intelligence, where AI is now able to hallucinate. For those of you in the, that would like to be a good dancer, but you're not a good dancer, you can always pick your perfect artist and just rotate in front of the camera and let AI imagine how you would look like if you were dancing like that professional dancer. Or the best example of AI nowadays is a self-driving car, which there is a tremendous amount of money being thrown at it, and we are able to detect lanes, reason about the scene, detect urban objects, detect signs. This is actually in wheelchair. This car drove 80 kilometers without a single interruption of a human, and it was such an impressive job. So with that, I want to jump into my favorite topic on artificial intelligence, which is the application of artificial intelligence in mental health. In order to have a good symbiosis between human and machine, we should have a good understanding of what mental states are. Mental states is usually defined and influenced by our behavior, mood and affection, belief and perception, and cognition, all sorts of elements in the cognition, such as relaxation and focus, and the amount of usage of a working memory. For the sake of this talk, I want to focus more on the cognition side of the story and talk to you guys about how we're going to use AI to assess the cognitive load of human being. So, what is cognitive load? Nowadays, imagine we have more than 80 billion neurons in our head. Each one is creating an electrical signal around our skull. We want to find a way that we can capture this signal and reason about it. And with the help of neuroscience and the artificial intelligence, we have been able to actually dissect these signals into different frequency bands, where each frequency band is dominant when you're up to a certain task. Let's say, for example, if you're in deep sleep, then your delta band is most dominant. Or if you're awake and doing the routine stuff, then your beta band, which is frequency between 14 to 30 hertz, is most dominant. So the goal is to get these signals and send it to some module and achieve something, some gauge that tells us what's the cognitive load. With that, I want to show you guys the demo of this device that I'm wearing. We call this in our group Fitbit for the brain because we want to monitor our brain on a daily basis and assess our cognitive load. And this cognitive load is influenced by our attention level and meditation level. And if we switch to a demo, hopefully this is working. Oh. I'm using my phone. This is a problem with the live demos always. So now I'm going to share. That's my sister's baby. Okay. Now I'm sharing with you guys my attention level and meditation level. Hopefully I'm having some attention. Yeah, you see this here, and this is up on the right. You see on the top, you see different bands that are being extracted from my head right now, and you can see the dominant band, frequency bands. You have the radar chart on the right, on the left side, which shows the focus of which band is being dominant. And these two gauges are. This gauge is showing my attention level right now, and thank God I'm a little bit relaxed and meditating too. So. Now we can switch back to the presentation. Actually, I don't need to wear this anymore, so you guys see this. Okay, so imagine the possibility if you have access to something like this. As Andy mentioned earlier, this is the performance arousal level curve, where when you're relaxed, it's like a monk meditating, you're most likely on the left side of this curve. Or when you're composing a music, you get closer to the high performance and higher arousal level. At the Olympic champion is probably at the most performance at the right arousal level. And you certainly don't want to be in the top right. Especially there are many different stressful jobs, such as surgeons operating. They tend to fall on the right side of this curve. Our goal is to acknowledge when you go beyond your availability, your performance is being decaying because your arousal level is being too much, and assess that and try to bring you back to achieve the highest performance. With that, this is the technology that we are developing. We call it assistive intelligent machine, and it's basically assessing. It has a perception. It listens to your brain signals, and it uses some neural network mechanism, which I'll explain in a little bit. And as a result, if your cognitive load is saturated, it tries to decrease it by some form of intervention, by stimulating your nerve or having different methods to bring it down. Now, this can go beyond individual. The cognitive load assessment can go beyond individual. It can be at the team level also. This is an application that we're working on in the e-gaming, where right now they're using all sorts of methods to improve the players' performance. Right now, for the sake of this talk, I'm going to focus on the EEG signal. This is an example of in-ear EEG. They basically plant this in-ear EEG into the headphones of the players, and they listen to their head and then try to see whether somebody is saturated, and they can perform better or worse if you give them more task. Now, this would have a very good application in the team sports or even in the operating room. For the surgeons, imagine if before you enter the operating room, you would have access to the cognitive load of the people who are involved in the surgery. Somebody might have some personal issue, and cognitive load of that person might be skyrocketing. And you don't want to have that person as your partner during the surgery. This would be a very effective thing. So this is an example of the same thing in the game of
now ready again.
In this game, it's a very popular game where 5 people playing against 5. And this the view that you see. This is also supposed to be a video on the left side. The person who's playing this game would have access to all his teammates' cognitive load. And as you see, those are the cognitive load of his teammates. And this is the player right now in the bottom left. And as they're playing this game, you can see, if you turn the volume up, you see something is happening. And as a result, you see somebody is not doing well, and that's because the cognitive level of that person is saturated. This can actually help.
He's so far back. Look at this. He's playing so safe. He knows he could be a target.
Not being found. A few more attacks will knock down the inhibitor. The flash forward. Look for the play. Not going to get anything for themselves. Goody blocks out a little bit. Here comes the Cataclysm, and it could be just
see a
that
third
for
person on the
SKT.
left.
They're forced to retreat the realm warp.
The cognitive level is saturated, and that's where the person
but
is
it does mean the damage
not
comes through
performing very
to
well.
Dex's turrets.
This is now ready.
Okay. Okay, now let's take a step back and talk about artificial intelligence. The simplest form of explaining artificial intelligence is that the AI is a system that can perceive information from nature and have some inference model, and based on that inference model, try to act. The simplest form of AI is a thermostat at home. So it senses the temperature. You can set the inference model for a threshold, and when the temperature reaches that threshold, it either turns the AC on or off. Then that's the act or the plan that it does. And like any scientific project, AI would abstract knowledge using, like in this case, a microscope. I'm making the example of cancer cells. And it tries to create feature vectors out of these cancer cells. And at the end of the day, it tries to create a line that separates the cancer cells versus the normal cells. So the core technology behind this is in how the AI does the pattern recognition. And this pattern recognition throughout history has gone through different phases. So in AI, we call it 3 phases of AI in this that does the pattern recognition. The first phase was handcrafted knowledge. You see these examples in the TurboTax example, or any protocols that if something happens, then do this. There is not much learning going on. It's a very definitive way of teaching robot how to do things. Which the beginning sign of this technology was about like 50, 60 years ago. And then we got into the learning mechanism. So the machine learning came in. And we were able to give the ability to the AI to see the world and learn. And then the third phase is the abstraction, is when the AI is actually not only learning, it's able to reason about the nature, which is what all humans do. It is a human level intelligence. Today, I'm mainly going to focus on the machine learning part of the story, which has occupied most of the artificial intelligence as we know it right now. So what is machine learning? Machine learning consists of 3 different elements. One is supervised learning, one is the unsupervised learning, and reinforcement learning. Unsupervised learning is when you give information to the robot and you assign a label for it. You give a cancer cell image and you say this cancer cell image is a cancerous, and you give another image and you say this is a normal image. So you provide labels to it so the robots can actually reason about what are the patterns that belong to each class. Another element of machine learning is unsupervised learnings. These are for the cases where you don't have labels for the data. You have to use methods such as clustering and methods that doesn't require one-to-one mapping between the labels and the data. The third one is the reinforcement learning, which instead of providing the labels or the clustering methods, you just teach the robot what's good, what's bad, and you let it go, and it would learn on its own over time, over experiencing with the nature. If it does something good, it gets rewarded. If it does something bad, it gets penalized. And by trial and error over time, it basically becomes an intelligent element. Now, something happened in the last couple of decades that boosted AI technology, which is not necessarily explicitly these guys. I want to point out what those factors were and have a little discussion on those topics. 3 things happened. Neural network algorithms was introduced. Computing power was increased, and massive data was available. I'm going to go into these 3 different points, and hopefully that would give you guys an explanation of why we are today and why we see the intelligent level that we see today from artificial intelligence. So let's start off with the neural network. Neural network is I should say artificial neural network, is a computing unit in electrical engineering and computer science, which is a mechanism to learn from nature. Back in the 1960s, Frank Roosevelt came up with the idea of he wanted to use the concept from simple human neurons and create an artificial version of this for learning method. Just the same way as a single neuron would collect information from dendrites and has some saturation level, and once it saturates to a certain threshold, it shoots the signal to the axon. He mimics the same exact same thing artificially. So given an image, we extract different cues from this image, information such as color, shape, size, and so on, and we create a artificial neural network to make a classifier out of this. How does this work? You have those information go into each node, and each one is weighted. For example, if the AI is about to classify the images, maybe the color is the most informative thing to classify between the cancerous cell versus non-cancerous cell. So then you see the weight of the color might be much higher in this here. Or it could be the size is a much more dominant factor in classifying this thing. So this is the weighted sum of these cues that you see in this artificial neural network. And once they get summed, it goes through some nonlinear function, which as a result, the Y would tell you whether it's a 1 or 0, whether it's a cancerous or non-cancerous cell. This was called back in the days perceptron. Many of you might have heard this. This created such a big hype back in 60s or 70s, and people thought that they solved the intelligence problem. This was up until, so this is an example of perceptron again. Perceptron is a linear classifier. And what it does is imagine each data point is one data point from each image of a cell. And the job is to create a line that separates out the good cells versus bad cells. As you can see, this is a linear model. That means you're separating two data sets with the line. Or if you're in the 3D space, you're separating it with the plane. This was glorious days until Marvin Minsky came and published a paper 10 years later and proved that there is a major problem with these perceptrons. And that was the fact that you couldn't simply separate out two data sets of green circles and red crosses with a single line. And with that, he began the AI winter. At the end of 70s, AI winter started, and it went on until early 2000s. Even though that he pointed out a problem about linearity issue of the perceptron, somebody else, Jeff Hinton, actually didn't give up. He decided to solve the problem. He decided to create a new artificial neural network that could actually use non-linearity in the model. So he started with the perceptron, and he simply just added another layer as a multiplier. Think of this as perceptron would be y equals x. This is y equals x squared. And simply with that, he introduced the nonlinearity to the neural network structure. But the problem is, in order to model nature's nonlinearity, we actually have to have a huge structure. We cannot just have a two-layer. We should have layers, hundreds of layers with thousands, millions of parameters. And in order to actually do something effective, you need to have a huge computing power, which wasn't existing back in the 80s. So no matter how hard he tried, he could never actually be successful until early 2000s, where the computing unit, the computing power was at the level that could address this kind of computation level. So what happens? We went from CPU to GPU. The difference between CPU to GPU is that CPU, think of it as a serial processing, which most of our computers would have, and GPU is a parallel processing. And with that change of concept, we boosted our computing power significantly. And in early 2000s, that's when Jeff Hinton could actually use deep neural network, and that's where we see lots of different good examples, which I showed in the beginning in the AI. Now, obviously data came in with the era of internet, but I want to point out, go back to the AIM topic, the assistive intelligent machine. Now, AIM is an AI system which assesses your cognitive load, and it either informs you that your cognitive load is too high, which I showed you in the beginning, or it can actually have an intervention, and it can actually stimulate you to bring your, to calm you down and bring you to the right arousal state. Or it can actually intervene in terms of in getting involved in the game. Let's say you're driving a car and you're about to fall asleep, and the AI would realize that, and it would kick in the self-driving mode and takes the control from you from crashing. In this example, it's an example of playing game of Pong. You think of you're playing against a computer, which is a red dot, and you are the light blue, and your partner AI is the dark blue. If you're doing well on the top, you can see that the signals are not as high frequency, so my cognitive load is pretty low. And AI will sit quiet. It doesn't intervene. But the moment that it sees that my cognitive load is being high, which as you can see in the score of the AI, the computer is 10-1, then it tries to help me out. It gets involved and tries to form a partnership with me. Okay, so how does it work? In more details. I promise not to go into too much details, but think of it as the simplest way of explaining this is that our brain signals get collected. We dissect these signals into different frequency bands. We send these frequency bands into a very deep neural network structure. As you go deeper into this neural network structure, think that you're abstracting different knowledge from this signal. If I'm explaining an apple, maybe I can, the first layer would say the apple is red, or it describes the color of it. The next level would describe the taste of apple. The next level describes the smell of it. So we have this EEG signal. As you go deeper and deeper into this neural network, we keep extracting different cues from this signal. And at the very end, we make a classifier which shows the gauge of where your cognitive state is. And with that, this is almost the last slide. I want to point out something that we are heading in the near future, and that's visualizing your imagination. This is a technology you're going to be seeing in the next 10 years. Just the same way as human neurocortex 6 system, when we see something in our visual cortex, the information gets abstracted in different layers. We want to mimic the same thing, but in the reverse way. So we get that EEG signal, we decode it with those neural network structure, that when you're thinking of the car, we can display you a car. And we have tremendous amount of success doing this right now. As of right now, we are at the point that their computers can actually hallucinate on their own. And as a result, you see, can we click on this video, please? The clicker is not working. What you see here is a result of AI hallucination. This is the hallucination about the horse, hallucination about the kitchen, hallucination about the living room, hallucination about the motorbikes. None of these images have been existing. This is all purely hallucination. We use 220,000 images from the scene to teach each concept to the AI, and we ask him, now hallucinate something new for me. I tell you hallucinate horse for me, hallucinate horse. I tell you hallucinate cars, it would hallucinate cars. And we are very close to connect this hallucination, to control this hallucination with our minds. That's the part that is still missing. This is the uncontrolled hallucination. Very soon, we'll be able to use our mind, use our brain signals to control this hallucination so that when you think about something, precisely that thing would occur. Okay. Oh, the applications of this are vast. You can have an application in military, you can have an application in medicine, sports, and our goal at AIM is to provide this Fitbit for a brain for everybody. We want to empower people with a device that they can assess their cognitive load in real time and try to have some form of intervention, either ask for AI for the intervention or inform them for themselves to do the better job. And with that, I want to end with my favorite quote that says, throughout history, we have used our mind to build and improve things. Soon, we'll be able to build things that improve our mind. Thank you.